So last week we had a lot of fun with the many matching. We had pineapples, pine cones, flowers, and ferns, and you guys found more stuff that followed the very natural patterns like Fibonacci numbers, fractals, and many others, right? So this week what we're going to do is what happened in the last 1 week in sports world. Anybody follow us? The World Cup soccer has started, right? Now, it's interesting, the rest of the world calls that football, but in America we have American football, so we call it soccer. But the rest of the world call it football. So do you know what this ball is?
Soccer ball.
Soccer ball. Because of the soccer World Cup, so let's have some fun with the soccer ball. So what do you guys think is the shape of the soccer ball? A sphere, right? Looks spherical, right? Any other ideas? Come on in. And you are? Pranay, come. Sit anywhere. You can sit in the front or second row anywhere. Okay. So we just got started. So because the World Cup soccer has started this week, we are going to talk about soccer. Okay. So if you got a soccer ball here, you actually have 2 soccer balls. Okay. The size 3 and size 4 soccer balls. Actually, my kids they go to soccer, so the coaches wanted different size. We got them. Now, I was just asking, what do you guys think is the shape of this? And sphere, right? That's the most common response. Observe carefully and see if you see anything else. Pentagons and hexagons on this. Do you see that? Pentagons and hexagons? Right? So, by the way, you're not the only one. If you ask this question to anyone, the first answer is that it's sphere. But if you watch carefully, there's more pattern to it. There are pentagons and hexagons, alternate pentagons and hexagons. There is a name for any solid or any 3-dimensional object made of these polygons. Pentagons and hexagons are called polygons, right? There's a name for that. Do you know what it is? Yeah? They're called polyhedrons. Did you hear the name ever? Polyhedron. Let me write. Okay? Now, the reason why you would not, the common response is fear, there's 2 reasons. The reason why we don't usually recognize this polyhedron straight away. One, to make that point, let me show you another shape. Okay, look at this. What are these? Dice. Some colorful dice here. Okay. What do you think is the shape of this particular die? It's a pyramid. Okay. You can tell that clearly. We don't call this a circle, but a sphere, right? This is also polyhedron. The definition of a polyhedron is a 3-dimensional or a solid object with a closed solid object with all its faces being polygons. If all its faces are like a triangle is a polygon, right? It's the smallest, simplest polygon. You can have squares, pentagons, hexagons, octagons, decagons, dodecagons. All those are called polygons. So this is a polyhedron. This is also polyhedron. But if you look at this, and let's say look at this one, right? This is also made of all triangles. Do you see that? This is also polyhedron. Both of these are polyhedrons. But do you see this is a little bit more rounder than this? So what happens as we increase the number of faces of a polyhedron? If you increase, this has actually, I think 1, 2, 3, 4, 5, this probably has 20 faces. This has actually 32 faces. Okay? Each one is called, each is a face. Is a pentagon or a hexagon is a face. If we keep increasing the number of faces to 100, 1,000, 1,000,000 faces, 1,000,000 small faces, what happens? You look closer and closer to a sphere, right? That's one reason. Because this has already 32 faces, right? As it's very close to being a sphere. There is a second reason. The second reason is that it will become more clear if I show you this picture. Look at this picture of these two. Okay? Do you see the picture of two different things here? This is the first one. The second one is the exact soccer ball picture. The first one, you watch carefully. That is also made of pentagons and hexagons. But, do you see any difference between the two? The difference is, because in a soccer ball there is air pressure inside and the material is kind of elastic. If you look at each of the pentagon and hexagon, they are not exactly flat. They are kind of curved, right? Because of the air pressure, it kind of becomes rounded. So it is not actually completely correct to say that this is a polyhedron. This is kind of polyhedron, but it's kind of a rounded polyhedron. So it's called a spherical polyhedron, as opposed to this first picture here, which is a pure polyhedron. That is another reason why it looks like kind of sphere. So this is a spherical polyhedron. Okay. Now, what I'm going to do is, let's look at, let's observe this a little bit more carefully. So let's call it a polyhedron for now. It's a kind of spherical polyhedron. Let's call it polyhedron. Okay. I want to find a few important characteristics of this object. Okay. Soccer ball. The shape of a soccer ball in the spirit of FIFA World Cup. Okay. There is actually, mathematically speaking, it has an even more accurate name. It's a polyhedron, but they're different. This is a polyhedron, this is also a polyhedron, right? But they're not in the same shape, right? So there's a name for this particular shape that is made of pentagons and hexagons this way. That is, and it's a very, it looks very complex name, but I'll explain in a few minutes why it's called. It's called a truncated icosahedron. That looks very complicated, right? Don't worry for now. We'll come back to that. Why is it called that way? And it will become, after we go to the rest of the material, it will become obvious. Now let's try to have some fun with this. So how many faces do you think it has? Each face being, each pentagon and hexagon is a face. How many faces do you think it has?
32.
Because I already told you, right? Of that, can you tell me how many are pentagons and how many are hexagons? Let's try to count carefully. Okay, let's start with the top. There's one top pentagon here. I'll keep it this way, easy to count. There's one top pentagon here, there's one here, right? There are two. And then, if you observe carefully, there are kind of two layers of pentagons, black part, all the black. There's one layer here, there's another layer here. So if you count, 1, that is 2, and then 1, 2, 3, 4, 5 in the middle, the top here, then 1, 2, 3, 4, 5 here. So 5 plus 5 is 10, 10 plus 2 is 12. So 12, so it has 12 pentagonal faces. They're all regular pentagons. Do you know what is a regular pentagon? A regular polygon means all its sides, all its edges are of the same length and all its angles are also same. So they're all regular polygons, right? So, and how many hexagons do you think are there?
24. Wait, sorry.
You're doing 32 minus 12, right? Which is 20. 20, 32 minus 12. But you can also count, okay? So 20. But you can easily count. When you're counting, you got to go in an order. Don't randomly count, then you'll lose. If you put like this again, you can see that around this pentagon, there got to be 5 hexagons, right? We're facing each face, along each face, there's 6 up there. Similarly, there are bottom 6. Alright, so, 5 plus 5 is 10. And then if you count in the middle, carefully count 1, 2, 3, 4. When you come all the way, there are 10 more. So 5 plus 5 plus 10 is 20. So the 20 plus 20 hexagonal faces to make a total of 32 faces. Now that is one of the important characteristics of any polyhedron, number of faces. Number of faces are the number of polygons it's made of. There are two other attributes which are important. Can you guess what else could be an important, apart from faces, what else can you count unique about any polyhedron? Can you count the number of point coordinates? And do you know mathematically what do we call coordinates as? Coordinates.
Oh, vertices.
Vertices. Edges are the lines that connect faces. Vertices are those points which connect edges. So how many edges do you think this has? A lot. Okay. To make it easy for you, I'll tell you. So we want to find vertices and edges. After you go home, take a soccer ball. Okay. Yes.
I think I know how many there are.
Okay. Tell me.
Edges, not vertices.
Okay. How many edges?
They're the same. There's 180.
180 edges.
No.
I know.
Yeah, 180.
Okay. Tell me why did you say that? You're using some math. Good. I'm glad. Tell me why.
Because hexagons have 6 edges
Right.
and pentagons have 5.
Okay.
And they have the same amount of edges as vertices, so
Right.
it had the soccer ball.
So
has-
you did 5 times 12, which is 60, plus 6 times 20, which is 120, right? Is that what you did?
Mhm.
So 60 plus 120 is 180. That's smart thinking.
But what about the common ones?
Right. Except that you made one minor mistake. That is, if you observe carefully, every edge is counted twice. Because every this edge is part of this face, also part of this. This edge is part of this and this. This edge is part of this and this. But your approach still works. So because of that, what do we need to do to find the real edges? Divide it by 2. Because every edge is exactly counted twice. Because no edge is part of 3 faces. Right? Every edge is part of exactly 2 faces. So you counted them twice. So 180 divided by 2? 90. But that's smart thinking. I like that. Instead of just counting, you use math. That's very good. So number of edges is equal to 90. Good. I like that. Yes, Aparna.
There are 60 vertices.
How did you say that?
Because 5 times 12 is 60.
Right?
And there's 12 pentagons, and each hexagon and pentagon,
Good, yeah, you're going the right direction.
I don't know how to explain it.
Yeah, no, but what she's saying is that if you observe carefully, every single vertex is a vertex of a pentagon. It's also a vertex of hexagon, but you don't want to double count. So if you take the number of pentagons and multiply it by 5, you get the number of total vertices. Do you agree? So the 12 times 5 is 60. Smart. You guys are actually teaching me. Excellent. So there are 32 faces, 60 vertices and 90 edges. I'll just call them F, V and E for now. Okay? In addition to that, I want you to observe one more thing. Okay? And keep this. We'll come back to this. Find out what is F plus V minus E. So what is the number of faces plus number of vertices minus number of edges?
2.
2, right? 32 plus 60 minus 90. That is equal to 2, right? We'll come back to that, okay? I'll keep that in the corner and we'll come back to that. Something very interesting, okay? Is it fun so far? Well, we're just getting started. Now what we'll do is let's lick this dice. Now I'm going to have you guys more fun. Know what we're going to do? I will give you one set of, where's my box? I will give, here it is. So I will give you one set of dice for each of you. These are yours to keep forever. Okay? But before you take, we are going to have some fun with each of those. Okay? They're different colors, but they're exactly the same. Same shapes. Is that everybody knows dice?
Yes.
Do you guys like die games? Did you ever play any games with dice?
Yeah.
Yeah? Okay. So how many dice are there in each of the sets?
6.
6 dice. What do you think is the shape of these dice? You already know, I answered it earlier.
How
What?
different?
They're all different, but they all have a common name.
Polyhedrons.
Polyhedrons. They're all polyhedrons because all of their faces are made of polygons. Okay. Now, here is a question for you. Of these 6, 5 of them have something in common, and one of them is an odd man out. It does not fit into that. Which one is that, and why? Observe that. Open it up. You can see they are yours. Yes, you already have an answer. Tell me which one.
The cube because
And you need to tell why.
the cube because it's not like it doesn't have as many it doesn't have as many polygons as the other.
Okay. So, Pranay, right, thinks that the odd man out is the cube because the cube does not have as many faces as others. Do the rest of you guys agree or disagree?
This one has less than the cube.
See, Shravani says that this has even less number of faces. A cube has how many faces? 6. This one will come to its name in a second. How many faces does it have? Only 4. 1, 2, 3 at the top and 1 at the bottom. So how can you say that this is odd man out because this has less faces than anything else?
I have another reason. This the cube is the only one that has a square as one of its polygons.
Okay, so what? I can tell that this is the only one that has pentagons. So is that odd man out because that is the only one that has pentagons? All good answers, but I'm looking for there's some, and it's hard for you guys to answer because you don't know what it is. But that's an important thing that we're going to get into this class. Okay? So to answer that question, come on, see, we got started. You missed some fun, but you can catch that in the video. I'm going to give you some dice. Do you like die games?
Sure.
Okay. The rest you can watch the video. Okay. So what we are doing is open them up. There's 6 of these dice. Okay. Of these 6 dice, 5 all of them are called, the shapes are called polyhedrons. Okay. Polyhedron is a 3-dimensional shape, or we also call it solid shape, solid geometry shape, where a closed 3-dimensional shape with all its faces still are polygons. It's called a polyhedron. So all of them are polyhedrons. But out of the 6 polyhedrons, one of them said is an odd man out, and try to find out which one is that and why. And they gave some guesses so far. Yes, Jenny.
This one is the only one with more than one number on each face.
Okay, yeah, okay. I'm asking about the shapes, not the numbers. Okay? But good try. More interested in the shape, not the numbers. Okay, to answer that question, what we're going to do is, let's go through each one and understand each of them in detail. And there's a reason, and each of them has a lot of history behind them. And those 5 of them which are together, they actually were studied by mathematicians for thousands of years. And they have some very special properties. They're found in nature. They're also found in arts and architecture everywhere. The more we study, and there are books written about them, there are PhD done about it. They're actually people who spend their lifetime on this. And there's some mathematician names given to them. So they're very special. Okay? So, but to really get to that, let's go through each one. Okay? We'll start with the easiest, simplest ones. Now, depending on whom we ask, one might say that this one or this one is simplest. Okay? This one, probably because we are most familiar with it. Of all these shapes, the one we are most familiar with is this one, right? It's a common cube. Everybody's familiar. But how many faces does the cube have?
6.
6. But if you observe this one, this is probably not as common as a cube, but probably most of you would have seen it some places. Right? What is this shape?
Pyramid.
It's a pyramid. What kind of pyramid?
Triangle.
Triangular pyramid. It's a pyramid with the base as a triangle. So triangular pyramid. Good answer. Now, what kind of triangles are these?
Equilateral.
They're all equilateral triangles, which means that they all have same side line. Do you think all these triangles are also of exactly the same shape and size?
Yeah.
All the four? The four triangles, right? And so let's write its characteristics before jumping to the answer. So we'll take each shape and we'll write about it, and we'll find some common attributes about that, including this interesting thing. Don't forget this. We actually had some fun with soccer balls before you came, and we were counting the number of faces, vertices, and edges. The soccer ball is also kind of polyhedron. It's made up of pentagons and hexagons. We found the number of faces, vertices, and edges, and we found that f plus b minus c, number of faces plus number of vertices minus number of edges, is 2. Right? So let's try to find this for each of the other polyhedrons as well. So let's start with this one. Because the simplest, it has least number of faces. Okay? And we'll try to use a different color for each one. So this one, I'll try to draw the shape, although it's harder when we go to the bigger shapes, but this one is a triangular pyramid with an equilateral triangle. Right? I'm not good at drawing, but hopefully you get what it is, right? So we just said that it has 4 faces, and all faces are exactly similar equilateral triangles, right? So it has a special name. And the way we name these are based on the number of faces. And because it has 4 faces, we call it a tetrahedron. Anybody heard this name earlier? A tetrahedron? Tetrahedron. Now tetrahedron means, in Latin, tetra means 4, hedra means face. A tetrahedron is 4-headed solid object. Okay? It is also called a regular tetrahedron. Regular means that all faces are exactly same. All faces are same regular polygons. So the regular polygons, like an equilateral triangle is a regular polygon because all sides are same, right? But they're also same. Unlike a soccer ball, which is also made of regular polygons, because every face is either a regular pentagon or a regular hexagon, but it is made of 2 different shapes, as opposed to this one, which is made with all with same equilateral triangles, with the same shape, right? So this one is called a regular polyhedron. This one is not a regular polyhedron. The reason is it does not have the same shapes for all faces. Okay? So we call this a regular tetrahedron. Although they look very, very different, there's something in common. They're both polyhedrons, but this one is a regular polyhedron, the other one is not a regular polyhedron. Okay? Now, to define a regular polyhedron, it needs to meet 3 conditions. 1, it should be made of all regular polygons. Okay? Both of these meet the conditions. Right? The second condition is all those regular polygons should be exactly same size and shape, which is meant by this regular tetrahedron die, but not by soccer ball. So the soccer ball fails the condition of regular polyhedron. It also needs to meet a third condition. The third condition is if you take any vertex, okay, of the polyhedron, it should have exactly the same number of faces and same number of edges going out of it. If you look at this has 3 edges, 1, 2, 3, right? It also 3 faces going out of it. If you take one in the bottom here, that also has 3 edges going out, 3 faces going out, right? That will not work for soccer ball because they're pentagons and hexagons, right? So this one met all the 3 conditions. Now let's do the same thing that we did for soccer ball. What we're going to do is number of faces will make a table. And if you want, you can write it also. You know, number of faces, number of vertices, and number of edges for each of these. Okay? So I'll need some help from each of you. And this is a really easy one. It gets harder when we go to the other ones, other shapes. How many faces does it have? We have talked about it. 4 faces. How many vertices does it have? Aparna? How many vertices does the shape have? Count. You have it. Take your tetrahedron shape, the one with 4 faces. Anyone? Tell 4 vertices, that's easy. How many edges does it have?
2.
Edges. Do you know what is edge? Edge are these lines that connect faces.
4.
Let's count. 1, 2, 3 at the top. 1, 2, 3 at the bottom. 3 plus 3 is 6. There's 6 edges. Okay? Let's keep it there. So you understand what a regular polyhedron, and we took the simplest of the regular polyhedrons. Now let's take the cube. Oh, by the way, what is f plus v minus e? 4 plus 4 is 8. 8 minus 6 is
2.
2. Interesting. You take a soccer ball, which looks much more complicated. You look at a small die, they both have the same number. Let's see what happens when we go to the other ones. Okay, next let's take the cube. A cube is made up of all squares. Is a square a regular polygon? Yes. Square, because all the side lengths are same, all angles are same. It is a regular polygon, right? It is made up of how many regular polygons? How many squares? 6. It has 6 faces. Do you think this is a regular polyhedron? Did it meet all 3 conditions? It's made, first condition is made of all regular polygons, and all the regular polygons are exactly same shape and size with their all squares, right? And if you look at the at each vertex, there are 3 lines, 3 edges and going out and 3 faces going out. There are, so we call it symmetrical with respect to every vertex. Do you know what is symmetry?
Yes.
Symmetry means it looks the same way, right? So it is symmetrical with respect to each vertex. So it met all 3 conditions. So it is a regular polyhedron, right? Now, so what name do you think I should give to this? A cube, right? But it also has another name because it falls into the special category of regular polyhedrons. What do you think I can call based on its properties?
Regular hexahedron.
You are a genius. You are absolutely correct. Why did you say that?
Because it has 6 faces.
Exactly. We said earlier that tetrahedron name came from 4 faces and it's regular. This has 6 regular faces, so 6 is hexa, right? You know hexagon, hexa. So she made up a word, and she was absolutely right. So this is called a regular hexahedron. A regular hexahedron, otherwise generally known to humankind as cube. So next time when you meet your friends and play dice with cube, okay, ask them what is this shape. Say, tell them it's called a regular hexahedron, and they will think you are, for a moment they will think you are crazy. Then explain them why is it called regular hexahedron. Okay? You can even impress your parents with this regular hexahedron. Okay? But let's finish this table for this. How many faces does it have? We have talked about it.
6.
6. How many vertices does it have? 1, 2, 3, 4 at the top. 1, 2, 3, 4 at the bottom. So 8. How about how many edges? 1, 2, 3, 4 at the bottom, 4 at the top, 4 at the bottom, and 4 vertical, right? That makes it 12. What do you think is f plus b minus e for this?
2.
6 plus 8 is 14. 14 minus 12? 2. Magic. Okay? We're taking completely different shapes, but for all of them, so far we got the same number. And there's a lot of history behind that too. There's a very, very famous mathematician, he identified this property a few hundred years back. And in fact, there's more research about them. We'll come back to that at the end of the class. Okay, so we finished 2. Making good progress, right? How about this? So let me take this one because this looks a little bit less complicated than other ones. What does it look like? What kind of shape is this? It kind of looks like a 2 square pyramids put back to back, right? We cut this in the middle, right? Does it look like a square pyramid? The top will look with 4 triangles, 4 equilateral triangles at the top, and then a square which you can't see right now because they're put back to back, right? How many faces does it have?
8.
8. 4 at the top and 4 at the bottom, 8 faces. Do you think this is a regular polyhedron? Apply the 3 conditions. You can answer. Is it made up of all regular polygons? Yes, they're all equilateral triangles. Are all the faces exactly the same shape and size? All of them are equilateral triangles, so it met 2 conditions. And at each vertex, is it symmetrical? Are there exactly the same number of faces going out and the same number of edges? The top one has 1, 2, 3, 4 edges and 4 faces. The bottom one is same, but be careful, the middle one. Look at middle one also has 4 edges going out and 4 faces going out. It's symmetrical with respect to every edge. Now you can also have another one like this, but it is elongated, where if it is not an equilateral triangle, but if it is a kind of an isosceles triangle, then it will not be a regular polyhedron, right? You see, if you make it if you have isosceles triangles where you have longer sides over here than the middle, then it's not a regular polyhedron because it's not made of regular polygons. Now, what do you think is the name of this one? Now, all of you should be able to guess based on, we already know the pattern. What do you think could be the name of this particular shape based on this pattern? See?
Regular octahedron.
You guys are just geniuses. You can come and teach now. Right? This is regular octahedron. And you never heard about this earlier, but you can put together the names. I'm so impressed. A regular octahedron. Octa means 8, 8 faces. Very good. So we just proved that this is a regular polyhedron, and its name is regular octahedron. So let's find its F, B, and E. Faces, vertices, and edges. How many faces we already talked about it? 8 faces. How many vertices? 1 and 2, 1 at the top, 1 at the bottom, and 4 in the middle. So 6. Very good. How about the number of edges? 1, 2, 4 at the top, 4 at the bottom, and 4 in the middle. 12, right? So what do you think is F plus B minus C?
2.
2, magic. Right? Very good. Making good progress. So let me go to this, the one with pentagons. Okay? Everybody see this one with pentagons?
Yeah.
Okay. What do you think we'll call it? Does it look like a regular polyhedron? Think through the 3 conditions. 1, is it made up of regular polygons? 2, are all the regular polygons of the same shape and size? Right? It is made of regular pentagons this time. And all of them are regular pentagons, exactly same shape and size. And is each vertex symmetrical? Exactly same as all other vertices? Right? If you take any vertex, it has 3 edges going out and 3 pentagonal faces going out. Same, right? So it is a regular polyhedron again. Now, what do you think its name should be? It's a little bit harder, but try it. How many faces does it have, by the way? That will give a clue to its
10.
name. 10?
12.
Did you count? Careful.
Well, but by the pattern of that.
Count. How many faces? Aparna is good at this. Did you count or did you just use math to find it like last time? Huh? You counted, okay? So the 12 faces. 12 pentagonal faces. So based on that, what do you think its name could be?
Regular dodecahedron.
You're close. What do you think is deca?
10.
Deca is 10, but it has 12 faces.
Dodecahedron.
Dodecahedron, regular dodecahedron. And you just should become like, you should be writing dictionaries now. Right? Regular dodecahedron. Regular, four, regular. I'm not trying to draw this picture because I'm pretty bad at that. And you will not know what I'm trying. So, and you have a dice with each of you, so you should be able to see. Okay? So how many faces did we say a regular dodecahedron has? There is name, of course.
12.
12. How about the number of vertices? You use your logic. Number of vertices. You can count also, it's not that hard.
12. 16. 20. 16.
Tell me your logic.
Well, I put my fingers on the ones that aren't touched, like the one.
Okay?
Oh, it's. I think they already said it, 20.
Yes. Aparna said 20. We're talking number of vertices, right?
Yeah.
Okay? So how many number of vertices for this pentagon? 20? Okay, one way to count is hold one pentagon at the top, one at the bottom. Okay? That's symmetrical, right? There's one pentagon at the top, one at the bottom. How many vertices are there in the top pentagon? 5 obviously. How many are there in the bottom one? 5. 5 plus 5 is 10. Now count the middle ones carefully. They keep going up and down like this, right? Start at one place and keep going all the way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 plus 5 plus 5 is 20. Okay? Very good. So 20 faces. Sorry, 20 vertices. How many edges do you think it has?
30. 30. I mean 40.
30 or 40? Why 30? Explain your logic.
Because each face has 5 edges and each edge is shared by 2 faces, so you multiply 12 by 5.
5 times 12 is 60 because shared by each exactly 2 faces divided by 2. Same logic that we did for soccer ball. Right? So that is 30. Now what is F plus B minus C for this one? 2. Magic. 12 plus 20 is 32. 32 minus 30 is 2. Very good. Pretty good progress. Now let's go to this one with lots of triangles. Not that one. This one. Okay? Done with lots of triangles. Okay. Okay. This looks a little bit more complex than other ones, right? How many faces do you think it has? History? 20 faces? Tell me why. You're right, tell me why.
Because the highest number that is
See, she's so smart. Because these are number. Everyone has a number, unique number. Starting with 1, it goes up to 20. So 20 faces. Good, you're right. So it has 20 faces. What kind of faces?
equilateral triangle.
Equilateral triangles. So do you think this is a regular polyhedron?
Yes.
Why?
Because all the faces are like they have like an equal size.
They're all equilateral triangles, so the same regular polygons.
And they're the equal size. And then the vertices, they each have 5.
They each have 5 edges and 5 faces going out from that. So they're same. So any vertex cannot be distinguished from any other vertex. All of them are indistinguishable from each other. And hence, it is a regular polyhedron. Now, what do you think its name would be? It's a bit hard. You may not have heard of its name. Some of you may have. It has how many faces? 20 regular faces. So what do you think its name could be? It starts with regular, we already know that, right? Because regular polyhedron. So what is the name? We also know that it's going to end with a hedron. Then what's there in the middle? It's called a regular icosahedron. Anybody heard that? Probably not. Okay. So this is a regular icosahedron. A-I-C-O-S-A-H-E-D-R-O-N. Icosahedron. I-C-O-S-A-H-E-D-R-O-N. Icosahedron. Alright. So let's do the same exercise for this. How many faces? Obviously 20. How many edges? Sorry, how many vertices? How many vertices?
12.
12. Tell me why. You're right.
Oh,
I don't understand your logic.
because the way with the other one,
Okay.
each triangle has 3 vertices, so you see how many faces share the same vertex. And
Smart. Well, that's really smart, right? Because it's a regular polyhedron, every vertex is exactly similar to others, right? It has 20 faces. Each triangle, equivalent triangle, will have 3 vertices. 3 times 12, 20 is 60. But each vertex is shared by how many faces? 1, 2, 3, 4, 5. So you have to divide by 5. 60 by 5 is 12. This is really smart. You need to come and teach. Next time you conduct this, you can come and teach here. Okay? Okay? That is absolutely right, and it's good logic. It's right logic. Now, how many edges?
30.
30. Explain why.
Because if you add 20 plus 12 and subtract it by
This guy is super smart. Now he's applying this formula backwards. Right? How do you know that it's going to work? Just because it worked for others? What if it doesn't work? Any other way?
no,
You're right, but
counting.
all of the others they have like regular polygons that are like the same, they're equilateral, I guess. But this one doesn't, so this one won't equal 2, but all the others will.
okay. Your answer is correct. Although we do want to double check, right? Because we're not through this formula yet. We just observed it for a few of them. You can't observe for 5 and say everything else in the world will follow that. Right? It's too short, too little data to come to that conclusion. Okay? So, it is actually 30. Okay?
Oh, I know.
Say?
If you like count, you don't have to count all of them, but you can keep 2 of them and you can count.
One at the top, one at the bottom like this?
Yeah, and 1 and 2, and you know that there's 5, and then you can go to the ones in the side,
Yeah.
and you can say those are 5.
So there are 5 at the top, 5 at the bottom, that makes
Which
it
is-
10. Then 5 horizontally here, 5 horizontally here, and then 10 vertically here. So add up to 30. Yep. Or you can do, Chini, you did this logic earlier, right? How many triangles are there? There are 20 triangles. That makes 20 times, each triangle has three edges. 20 times is 60. But each edge is exactly shared by 2 faces. 60 divided by 2 is 30. There are several ways to do this. And so we can, because we independently calculate this is 20, now we can say that f plus v minus e is 20 plus 12 is 32 minus 30 is 2. Okay, so it was. Very good.
Um,
Yes.
Did we already do like the projects that got like last week? The
We went through that at the beginning.
Oh.
For you, if you want, we can check at the end of the class. Okay? So now, yes.
Is this one not regular?
There you go. She already found the odd man out. Right? So, do you guys think the sixth one that is left over here, do you think it is a regular polyhedron? Does it meet the three conditions?
No.
It actually does not meet any of the three conditions. Well, it does not meet actually, no, two of the conditions. One, it is not a regular polygon. It is not made of regular polygons because the kind of it has four faces, but two of them has one length, other two have another length, right? All the polygons are actually of the same size, same shape and size. They're just not regular, right? And also, the top and bottom have how many edges going out? 1, 2, 3, 4, 5. But if you take any of the middle ones, they only have 1, 2, 3, 3 edges going out, right? And hence, this is not a regular polyhedron. So this is the odd man out. Not the cube, not the little tetrahedron. They all belong to one category called regular polyhedrons. This one is not a regular polyhedron. Okay? Now, here is the real clincher though. What is so great about it? Oh, if these are regular polyhedrons, this is not, right? What is so big deal about that? Why did we spend so much time about this? Do you know why? The reason is, in the entire world of solid objects, in the entire world of three-dimensional objects, these are the only 5 regular polyhedrons. There's nothing else. We can try for another. In fact, I want you to try for the next 1 week. That's one of the projects. Try to see if there's a sixth polyhedron, sixth regular polyhedron. In fact, this is such a fascination for mathematicians and scientists for thousands of years. There are many volumes written about this. Some mathematicians spent their lifetime on this. And some said the whole nature is made up of this because they're so symmetrical. Others are not so symmetrical. Their faces are symmetrical, their vertices are symmetrical, their edges are symmetrical. Some mathematicians actually propose that the nature is made up of this. I will come to that in a minute. And because they are so unique, right? There are obviously a lot of mathematicians spend a lot of time and there are special names given to them. And last week we talked about one. Do you remember the time history, the mathematical history timeline that we followed? Aparna, you weren't there, you can see the video. So we went through, for the last 12,000 years, we kind of looked at how mathematics progressed over a period of time, right? We went back all the way back to 10,000 BC, right? That's 2000, we have 2000 AD, 2000 years after 0th year, and 12,000 years before that. And we kind of looked at how math might have been used by the earliest, some of the earliest human beings before any modern science evolved. Before, in fact, even writing evolved. When there was no writing at all, do you think people needed numbers? Do you think people needed numbers or mathematics? Probably a little bit, right? Even people before they settled down, right? If you try to understand the evolution of human history, okay? That's not math, even if you just look at history. Before people settled down for agriculture, that was a huge breakthrough. Before that, people used to go for what? They used to call as hunter-gatherers. They used to hunt for other animal food or gather fruits and vegetables, and that's probably made up their whole day, right? People used to live. Man, you're so lucky to live in this world, right? You don't need to spend a whole day trying to get food for the day. That's already there, right? And in fact, your parents are getting, but your parents are not just trying to get the food the whole day, right? They're actually working somewhere, and it's all because of so many scientific innovations that happened, especially agriculture. We take it for granted today. That imagine the time when there is no agriculture. The only food that you can get is by either take a weapon, go get an animal and eat the food, or get vegetables or fruits from trees that are naturally available. Right? From those days, do you think they needed math?
Yes.
Yes. What do you think they could have? How they could have used math?
One thing is that if they wanted to find the time of the day, they could kind of, well, never mind. If they want to count like how much you have to divide, so
That's a good one.
enough food will be for each member of their family.
Right. They would have at least needed to count unique numbers. I got 5 animals today, and we have 10 people in the family. I don't know whether they had families like that, but you needed some kind of counting. So you needed numbers like 1, 2, 3, 4, 5, 6, 7, etc. Right? That's why those numbers are called natural numbers. They are naturally required by people. Do you think they needed 0 at the time?
No.
Do you think they would have said, I got 0 animals today? No, I got no animals, right? You did not need it. That way 0 came much later in the timeline, but you needed counting numbers. From those days, we went through a lot of history, and we spent some time from about 500 BC to 200 BC, we said there's one particular civilization that kind of did a lot of advance in mathematics and science and philosophy, etc. Do you remember who they are?
The Egyptians. Greek.
We talked about Greeks. In fact, Egyptians, Mesopotamians, Indians, Chinese, those civilizations are even before Greeks, and they actually did a lot of advance in math. But unfortunately, a lot of it is lost to the history. It's not documented well. But the Greeks did actually a lot of work, and they actually documented, and that's actually foundation for most of the Western culture today. The ancient Greeks which lived between, they lived probably between 900 BC to 100 BC or so, but their classic period, golden period, is about 300 years between 500 BC to 200 BC, when they did a lot of research on a lot of different topics, including math. And they were fascinated by these regular polyhedrons. Earliest days, probably only 2 regular polyhedrons are known, because these are the easiest ones, the cube and the tetrahedron. Others, and these were probably known much before Greeks too. They were probably known to Egyptians, the ancient Egyptians, and Indian, Chinese civilizations, and Mesopotamians. But Greeks wanted to find all possible regular polyhedrons, and they did find that these are the only possible ones. In fact, there is one particular philosopher, Greek philosopher, we talked about him briefly last week. He did so much research, and in fact, he said nature is made up of 5 elements. Okay? And which, today we know that there are a lot more elements. And in fact, that's not just Greeks. Even Indian philosophy in those days talked about 5 elements. In fact, even today we talk about it. You may ask your parents. There's something called Panchabhutas. Panchabhutas means 5 elements. Water, fire, sky, land, and one more. Wind. Okay. So these 5 are called Panchabhuta. Greeks also believed the same. And it so happened that the 5 regular polyhedrons, they said each of them represent one natural element, and the whole nature is made up of them. While a lot of Greek philosophers actually contributed to that, one particular person who documented it and well known for it, his name is Plato. Now we talked about Plato briefly last week. You remember? He actually had a quote. Remember we said he actually used to have an academy like this, he used to run an academy, he used to teach. And outside his academy said there is a slogan, do you remember what it was?
No one arrogant in mathematics may enter.
No one ignorant of mathematics may enter here. So he thought mathematics is required to learn anything else. Okay? And these solids are actually named after him. So these 5 together regular polyhedrons are also called, named after him. What could have been this if it is named after him? They are called Platonic solids, named after Plato. They are called Platonic solids. If you go and research about Platonic solids, these are the 5 things that you will get. Okay? And there was another mathematician from the Greeks who actually wrote books about mathematics and especially about geometry. And for Greeks, mathematics essentially meant geometry. There's a lot of research on geometry. We'll talk about different kinds of mathematical subjects in the 4th week. But Greeks especially believed in geometry. And this particular other mathematician talked about his name is Euclid. 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 He wrote a number of books, in fact 13 different volumes of books that he wrote on math, on geometry, and he called them elements. The names of the books is elements, 13 books, and he covered, in fact today a lot of geometry that you're going to learn when you go to middle school, late upper school, upper elementary and middle school, most of the geometry based on what Euclid taught, wrote more than 2000 years back. Now until actually a few hundred years back, this was the only math followed by Western countries, Europeans. Now later in what we call as Renaissance, we briefly talked about in the math timeline last week, from about 14th century to 17th century, other mathematical concepts like algebra and later calculus, etc. came. But otherwise, Euclid's elements were the standard mathematical text followed from Greek time to until about 400 years back. That's the only thing which is followed. And one of these, in his last book, he actually spent a lot of time explaining about Platonic solids or regular polyhedrons. And he proved that these are the only 5. One might wonder, right? Why only 5? Doesn't it sound odd that you can have so many, you can make so many shapes, but only 5 of them are possible, which are regular polyhedrons, right? In fact, we are going to see a video why only 5 or nothing more. And Euclid actually described that. So at this point, let's switch off the lights for a second, watch this video. We'll actually watch 2 videos. The first switch only, the bottom one. Yeah. Actually, other ones also, all bottom ones. So let's switch over.
These are the Platonic solids, named after the ancient Greek philosopher Plato. Platonic solids are a very special type of polyhedron. Polyhedron is a solid constructed by joining polygons along their edges to enclose a region of space. Polygons then become the faces of the polyhedron. When all of the edges of a polygon have the same length, and all of the angles are the same, the polygon is regular. The Platonic solids are constructed from such regular polygons. Platonic solids are characterized by 3 properties. All faces are regular polygons. All faces are exactly the same, or congruent. And all corners are exactly the same.
Right? The same rules that we talked about.
That is, the same number of faces meet at each vertex in exactly the same way. The cube is an example of a Platonic solid. All of its faces are congruent squares, and 3 faces meet at each vertex. This polyhedron is not a Platonic solid. Although all of its faces are regular triangles, and the faces are all congruent, 3 faces meet at this vertex,
See why it's not a regular
while
polyhedron?
4 meet at this one.
Is it?
This solid has
triangular
2 different
pyramids
types of
put together.
vertices. This figure is not a Platonic solid. All of the faces are the same, and the same number of faces meet at each vertex. But the faces are not regular polygons, since not all their sides have equal length. The faces of this polyhedron are all regular polygons, and 4 faces meet at each vertex. But they're 2 different types of faces, squares and triangles.
Remember, this one will come back
So
to
this is
kind
not
of solids
Platonic solid.
later in the class.
Over 2,000 years ago, a mathematician named Euclid wrote a book called The Elements. This book is the basis for most of today's high school geometry courses. The grand finale of The Elements is a section about the Platonic solids, in which Euclid shows there are exactly 5. His explanation goes something like this.
Watch this carefully. Explain why.
The simplest regular polygon is the equilateral triangle. How can equilateral triangles fit together to form corner pieces of Platonic solids? 3 triangles can form a corner, and 1 more triangle closes the shape.
Okay, let's watch this one. It's important that you understand what is explaining here, because this is where they're going to prove that no more than 5 of these regular polyhedrons are possible. So this particular one, if you understand, is the basis for others. When you take a triangle, okay? A triangle, an equilateral triangle, right? Because it needs to be a regular polygon. What is the angle at each equilateral triangle? You know? What is the angle formed at each triangle? What is the total angle, total of all the 3 angles at a triangle? 180 degrees. So because it's equilateral, 180 divided by 3 is 60. They should all be 60 each, right? Agreed? Now, to make a polyhedron from a polygons, which are 2-dimensional, right? One way to think about this is, see how at any point, what is the total angle at any point? You guys know? 360 degrees, right? You guys know that? The total angle at any point, any one point is 360 degrees. Let's see how many of these let's start with triangles. So we'll take each of the regular polygons and see how many regular polyhedrons are possible. The smallest polygon possible is a triangle. So we'll start with a triangle. We'll exhaust all these polyhedrons, regular polyhedrons possible from a triangle. Then we go to a square, then we go to pentagon, then we go to hexagon and see how many are possible. Okay? For a triangle, this is 60 degrees. And we can put one triangle like this. Right? This is 60, this is 60. You can have another triangle like this, and you can have a third triangle like this. Okay? So when you have 3 triangles put together like that, each of them will make 60 degrees each, right? That takes 180 of the 360 degrees. So the angles between the gaps between them is also 60 each. So imagine a paper where you cut the paper to make 3 triangles like this and rest is gap. Then you can fold them so that the edges meet to make 3 triangles come together, and at the bottom then you can add a 4th triangle, and that's how that is made. That is one way to make it. Now what he is going to explain is, can we put 4 triangles here and fold them to make a regular polyhedron? Then you can make a 5, can we make a 6, can we make a 7? How many are possible with triangle? Then we'll take the same with a square. So let's continue and look at whether it is possible to have a regular polyhedron with 4 triangles.
Platonic solid with triangular faces. This solid is called a regular tetrahedron. Four triangles meeting at a vertex form a corner that looks like a pyramid.
So you can also make 4 triangles.
2 of these corners can join
You saw that one, right?
to
What's
form a
that?
Platonic solid with 8 triangular faces.
This one.
Notice that all the corners are identical. This solid is called a regular octahedron. 5 triangles meeting at a vertex form a shallow dome. Joining two of these domes will not form a Platonic solid, because not all of the corners are the same.
See, it's 5
Joining the two
triangles.
domes to a center band of 10 congruent triangles forms a Platonic solid with 20 faces. It is called the regular icosahedron. 6 equilateral triangles surrounding a vertex lie flat, so no more regular solids can be made.
Okay, so we could make regular polyhedrons with 3 triangles, that is a tetrahedron. We can make it with 4, that is the octahedron, and we have proved that we can also make it with 5, that is icosahedron, right? By putting with 5 of them, because when you put 5 of them, that makes up 5, because each of them makes 60 degrees. 60 times 5 is 300 degrees. There's still gap between them, and you folded the gap and you made the icosahedron, right? If you watch that carefully. But if you put 6 of the triangle, what happens?
All of the gaps.
All the gaps are filled. See, because 60 times 6 is 360 degrees. Now you got a completely flat paper. You cannot fold it. There is no gap to fold, right? And hence, it is not possible to have with 6 of the triangles. Do you think it's possible to have more than 6? You can't, because there is no gap to fit, right? So these are the only possible shapes, regular polyhedrons, using equilateral triangles. A regular tetrahedron, regular octahedron, and icosahedron. Okay? Let's go on, let's watch.
Made with triangular faces, because no more triangles will fit around a common vertex.
Now let's take the squares.
The next simplest regular polygon is a square. 3 congruent squares can join to form a right-angled corner.
Right? Because
Like the
90
corner
times
of a
3 is
room.
270 less than 360.
2 of these corners can be joined to make a cube. 4 squares meeting at a vertex lie flat.
Right? Because when you add 4 squares, that's 360 degrees, you can't bend it anymore. So with squares, there's only just one shape possible.
So the cube is the only Platonic solid with square faces.
Let's look at pentagons now.
The regular pentagon is the next simplest polygon. 3 of these meeting at a vertex form a corner.
You can make a corner, you can bend
4
it.
of these corners together form a Platonic solid with 12
That is
faces.
this one. 5 pentagons.
It is called the regular dodecahedron. 4 or more regular pentagons will not fit around a common vertex.
That will be more than 360 degrees. Can't make it.
Three regular hexagons coming together at a vertex lie flat.
Because there's already 360
So no more solids can be made with just hexagonal faces. Regular polygons with more than 6 sides won't fit around a vertex at all.
That's why they're exact. There are 5 regular polyhedrons. Anything is mathematically impossible.
There are exactly 5 Platonic solids. The tetrahedron, the cube, the octahedron, the dodecahedron,
And then, what is the fifth one? Icosahedron. Yeah, you can call it.
and the
Yeah.
icosahedron.
You can close it now. Okay? So now you understand better what are the 5 regular polyhedrons or 5 Platonic solids and why there are only 5 of them, right? Now, actually go to the next tab. Next tab in that So we studied each of these, okay? We understood that there are only 5 regular polyhedrons and nothing else is possible mathematically with a proof, right? Now, what we are going to do in a few minutes is, I want you to really touch and feel them. Not just with the dice, but actually you build it yourself. Okay? So we are going to go to a table and build maybe a couple of tables and build the regular polyhedrons, some of them yourself. I have enough for all of you to build all 5, but we don't have enough time to build all the 5. So we'll build 1 or 2 and rest you can take them home. I actually have print out and how you can make them, so you can do it at home, and that will be one of your projects to do it at home and bring it to next week. Okay, it will be a real fun project, and as you build it, you learn more about it. Okay, but before to do that, you need to learn one thing. How many of you know a net of a solid? Do you know when we say net of a solid, net of a three-dimensional object? Anyone knows? Sri, yes?
A net is like if you take all the sides and make them flat.
Right. If you open it up, if you unwrap it, if you take a cube, probably easiest to understand, right? You unwrap it like this picture. So for a cube, to make a cube, if you unwrap it into this how it looks, right? You can fold this way, you can fold this way, you can fold this way, but this one, you fold this and then this second part goes to the top. So to make any of these regular polyhedrons, you need to first have the shape drawn on the paper, cut it to the net, and then fold it in appropriate places and glue it. That's exactly what we are going to do. But to do that, I want you to watch a couple of videos on how to make, because you will appreciate far better when you see how it is being done. Okay? This is going to be using color papers. We'll have a white paper, so you need to do a little bit more, but watch this first. So first we'll watch each of them. So this is how to make a cube, which is relatively easy problem. For that, so for the net to make a cube. Right, you can close this and go to the next one. Which one is going to be good? Go to the next. The first few are relatively easy. When you go to the bigger ones, that's when it gets harder. So let's replay. This will be a tetrahedron. How to make a tetrahedron? This is also relatively easy. Once you have the net, you fold 3 of the triangles and then glue it together. Right? That's the net of the tetrahedron. Fold 3 of the triangles. That's right. Next one will be, I think, the octahedron. You need to bring it to the front. You need to bring it to the front. Yeah, it's already played. Replay. Okay, that's the octahedron. That's the net of the regular octahedron. This is a little bit more complicated. You have to fold the right folds to get the shape, otherwise you don't get the right shape. You have to fold each of them in the right shape to make. To close like a square pyramid from the top, a square from the bottom, and combine them back to back, you get regular octahedron. See that? Think of it like just 2 square pyramids put back to back. Next one is a icosahedron. It's an icosahedron. It's also made of triangle. Although icosahedron has more plus than dodecahedron, icosahedron is relatively easy compared to dodecahedron. The dodecahedron is made of pentagons. It's still triangle. but it's a little bit harder than the previous one, right? You can watch it, run it correctly. Think of it like 5 triangles coming together in the top, 5 triangles coming together in the bottom, and then you have 10 triangles in the middle. 20 triangles. 5 triangles in the top, 5 in the middle, and 40. 10 more in the middle. There's 20 triangles. Okay? It's a bit harder than others. Make sense? Let's go to the last one, which will be a dodecahedron. Dodecahedron is actually harder than icosahedron because they are pentagons. Its net will look different compared to all others. These are not pentagons. They will be 12 but small pentagons. The right hand cut and then point up. Let's go to one table. So I'm going to give one set for each of you. Each set has 5 sets of thick papers, okay, and so 5 polyhedrons. You will not be able to do all the 5 today. We will not have enough time. We'll do 1 or 2, and rest you can do it at home. That will be one of your projects. Okay, this is your set. This is your set. This is your set. Can you get 2 more sets, sir? Okay, so within these sets, what we are going to do is, let's start with the easier one, the tetrahedron first, right? And keep all the papers on this side because, so for tetrahedron and cube, it's not going to be that hard. And see this glue, okay? You cut on the outer edge, don't cut on the dotted lines, okay? Then it will all come apart. Cut on the outer edge, including the glue, because you're going to fold the glue, right? For these ones is easier when you go to the bigger ones, okay? Because it is only printed on one side, on the other side you cannot see where the fold is. Once you start folding, if you half fold, you cannot see where the fold is on the other side, right? To accomplish that, what I have is, I have tracing wheels for you. Where are our tracing wheels? So we have tracing wheels for you. These tracing wheels will help you cut perforations. You can make in the middle ones where the dotted lines are there. You can actually cut at the edges, or not cut actually. They make it right here. We're going to make perforations there. At the perforations, you can see it from the other side because once you make those, they're like dotted. Holes you can see on the other side, you know that you can fold it over there. But you would not need for the probably tetrahedron and the cube because they're relatively easy. So each of you take scissors, start cutting at the outer edge only. Everybody got a scissors? All 5 of them? Okay, very good. And here are the... So once you're done with this, you don't need it for now. For the other ones, you can make the perforations like that. I'll show you. You can keep continuing with that. I'll help this. So what you need to do is, you do this on just this dotted line. Okay? What happens when you do that is, and you don't need to do it for the outer, you just need to do for the middle ones where there's a dotted line. Now, you need to do it a bit harder so that you can see from the other side. See, do you see the perforations? You know that you need to bend there. Okay, but for the tetrahedron and cube, you don't need that. Does it make sense?
Yes.
All right, yeah. Now you can fold on the dotted line, fold on the dotted lines. All right, I can see some of you are already close to bend folding. And once you're ready, once you fold, you can glue it where it says glue under.
Are we on to use that or just
Which one?
that?
This one later. Are you done with? No, go ahead and fold that.
No, I mean for the other shapes, do we have to use that too, or can we just bend it with our hands?
So if you try to do it a dodecahedron with hands, what happens is once you fold, you can't see from the other side, right? Because there are multiple folds. Whereas for a tetrahedron, it is just one fold. So you can still see the whole thing from outside. For the more complex shapes, if you don't do that, you will not be able to see. Okay? Right, your question?
I don't have one of those.
You don't need it for this one. So what you can just
No, for the other ones.
I'll give you there are a couple of them. You can use this. For this, go ahead and finish this first. Everybody finish the tetrahedron first. And go all the way, glue it as well. And do it exactly on the dotted line. Okay? And fold it like this. Like this. Okay? And also do this force for each of those on the dotted lines. Like this. Right? And also do this. Dotted line. And now, so first mark all of them like this, okay? Then fold all three of them and then you can glue.
Do we fold this way or this?
See how where the glue needs to go, right?
Okay.
First go ahead and mark them, mark.
Did I make a mistake?
Yeah. No, you did not make a mistake. You just need to fold this out. So this, and then put the glue here. And just, oh, you don't want the glue. Okay, do it here. Put the glue here.
Okay.
Okay. So you did not make a mistake. You're good.
I don't get it.
Wherever it says glue under, put the glue here and then just close it. Make sense?
Yeah. It doesn't close like when I think I need more glue on this.
You're not able to glue it?
You glue only one edge first, you know.
So any
instead of
one
doing
edge,
all three.
any one edge, do it like, and just press that.
The glue dries really fast.
Yeah, so you have to do it fast.
Yeah, good.
See? As soon as you put the glue, so where it says glue under, put this glue. Okay? And then quickly go ahead and fix this now. In fact, these two you probably have to do it together, but you need to do both of them fast. Okay? Do this, then push it over here, and then just press hard. That's it. Then let it cure for a minute. Then you got your regular tetrahedron. Okay? Those who are done with,
I need help.
okay, I will help you. So, you came up to this, you're almost there. What you need to do now is, at any one of them, put a glue first. Like this, okay? And then quickly go ahead and fix it. Okay? Now having done this, do the, okay, let it push it so that Got that one?
Yeah.
Okay. Now go ahead and put the glue for these two. You need to do this together because once you do the other one, you will not have space. You need to put this and quickly go ahead and fix it.
Do you do this on all the dotted lines?
Yeah, let's do the cube next. So the cube, where is the cube? This is the cube. Cube is also relatively easy. You don't need to do it for cube also, right? Because you can still see almost all of them. So go ahead and cut the cube. Yeah, that's it. And then keep it down here. Okay, you should do that after some time. So that's your regular tetrahedron. Now go ahead and cut the cube. You done with the cube also? See? No. Why are you looking for it? Most of you done with the tetrahedron? Excellent. Go to the cube now. Do you guys want to go ahead and complete the cube, or because cube is relatively easy, maybe pause it and maybe you want to go ahead and at least make the perforations for more complex ones. You want to do that? Because cube you can easily do it at home. So I want you to understand, maybe take something that is a little bit more complex. Maybe take this icosahedron with the 20 triangles, okay? So, maybe some of you continue the cube because we only have only a couple of these perforations. So 2 of you continue, rest continue with the cube. 3 of you continue with the cube. You need to do it hard though, you need to push hard, otherwise you need to be able to see the perforation on the other side. See if you're able to.
Kind of, not that.
You can see some, but so you do it one more time, a bit hard. Do exactly on the line. Yeah, now it should be good. Okay, go ahead and do this one also. Yeah, I think you can see it now. Can you see it? Yeah, that's good, right? So that's enough. Now make each of these triangles also. And up and now while doing, make sure you don't have any other papers below, otherwise you'll make holes on those as well. If you have a clipboard, you can put it on a clipboard. Is this your clipboard? Put it on the clipboard and then do it. You have to do it hard. We'll just do it for a couple of minutes more and then we'll go back because I just wanted to get to understand how to do it. You can do the rest at home. We have a few more interesting things to cover today, but I want you to get to the fun of this and be able to understand so that you can continue it at home as a project. So this will take an hour, a couple of hours to complete all of them because more complex ones will take some time to get it to do really well.
Yeah, I can see it now.
Yeah, that should be fine. Okay. So that's okay. Now go ahead and continue your cube because rest you can do it at home.
Should I do the perforations on these two?
You can do it later. Let someone else do a perforations if they're done with the cube.
We can continue. You do it as a project at home.
So we're going to close in another 1 or 2 minutes with this. All of you got an idea of how to do this, right? Now, if you're not,
Pick up your extra paper and put it on.
so after you're not sure, right? If you get a doubt at home, just go to YouTube, okay? Let's say you want to see how on YouTube we always should do it to parents, okay? Because we don't want to get we only want to get the right content, right? So if you type on YouTube and you can talk to your parents, constructing, let's say you want to do icosahedron, constructing icosahedron from net, and it will show you the videos, okay? And you can watch that video as you do this, okay? Make sense?
Yeah.
All right. Otherwise, I can actually send the link for each of those 5 videos of how to make cubes, tetrahedrons, icosahedrons, dodecahedrons, and octahedrons, okay? All right. So in 1 more minute, I want you to close and come back to your seats so that we can continue the rest of the topic. We have about 30 minutes more. Okay, as you come, what I want you to do is make sure you collect all your papers. Any of the solids that you already built, take them with you. Okay? And make sure if you brought the dice here, take your dice. And next week, when you bring this project, you put it in a bag. Because when you make all 5 of them, they're solids, right? They're not like paper.
They'll be 3-dimensional objects.
They're 3-dimensional, so you put it in a bag and bring them, okay? And the one who makes the best one in the entire, across all 3, will have some special prize for them. So spend some time, it will be fun. You know, there is another way to also make the polyhedrons. I don't know whether you guys thought about it. Do you think there is any other way to make this instead of using this paper? You know what you could do? You can use toothpicks and gummy bites or any other marshmallows and make also. Okay? And in fact, try some of those. Try some of those to make at least one of these polyhedrons, maybe one of the more complex ones, with toothpicks and marshmallows. Okay? Alright, with that, close up and come back to the seats. Alright guys, come back. Take your stuff. Make sure you collected all the papers because you're going to get papers at home to make the rest of the polyhedrons, regular Platonic solids. And keep your dice. Your dice will be a good guide for you to see the final shape. Make sure that the paper solid matches with the die shape. Okay? Now, as you settle down, we saw this Platonic solid. In fact, these are so fascinating, as we talked about. Even today, a lot of mathematicians still spend a lot of time, and it's found not just in mathematics. In science, there are certain scientific elements which are found to be following the shapes of Platonic solids. And as you said, they also capture the imagination of many artists. Like during Renaissance, Leonardo da Vinci spent a lot of time building artistic objects using Platonic solids. Some architects, some of the buildings, they actually use this. Now you may not be paying much attention, but next time you go to any museum or any place, see if there are any actually Platonic solids or polyhedrons or regular polyhedrons there, and you will find them. And you can tell about shells. That's a regular icosahedron. Nobody else might understand, but you can explain to your parents why is it a regular icosahedron or a dodecahedron. Okay? But as interesting as the Platonic solids are, there are many other types. There's one particular type which is equally interesting and found very often in both nature as well as in art. And these are named after another Greek philosopher. And you might have heard his name. These are called Archimedean solids. Anybody heard about Archimedes? Yes. Where did you hear from him?
Like in a lot of books.
But a books, Archimedes is known as one of the greatest mathematicians ever. He He lived more than 2000 years back. He came this close, very close to inventing one of the greatest mathematical inventions ever, which was finally invented about 400 years back, 500 years back by Newton and Leibniz together. It's called calculus. And the calculus is certainly one of the greatest innovations in math and science. Without calculus, we will have engineering would not be able to today's advanced engineering or any of the advanced fields, sciences will not be able to analyze without calculus. Calculus here, and we'll talk about that on the 4th week. But he came this close, very close to inventing calculus, although he did not take the final step because of the limitations at that time. And some of you might have heard his story, Eureka story. Anybody heard Archimedes' Eureka story? It's very fascinating. Maybe we'll talk about this. It's more about the science. It's a very interesting story. One day we'll do discovering the beauty of science, and we'll talk about that as one of the stories.
I'm not sure if this is the mathematician who ran outside.
Yes.
With
His king asked him to find whether the golden, supposed to be golden crown that's made, whether it's pure or not. And there's no way to find without breaking it in those days. And he came up with a method. He got the idea in his bathtub. And he runs Eureka, right? We'll talk about this another time. He's the same Archimedes. He lived in within the Greek kingdom, a place called Syracuse, and is considered one of the greatest, one of the three greatest mathematicians in the world ever. But we'll spend more about that some other time. And this set of solids are named after him. They're called Archimedean solids. The difference is that similar to Platonic solids, the difference is that, and in fact we saw a couple of them earlier today. They are made of 2 or more regular polygons. Everything else still works, but they're made of 2 or 3 regular polygons. So they're polyhedrons made with 2 or 3. Can you recollect anything that we talked about that fits the definition? The soccer ball. Say it loud. You're absolutely right. So do you think the soccer ball meets that condition?
Yes.
Because it is made of 2 regular, they're all regular polygons, but some are made of polygons, some are made of hexagons. So this is one of the Archimedean solids, one of the more famous of the Archimedean solids, and it's actually the actual soccer ball used. As the soccer games are happening in Brazil, World Cup football going on, this is the geometry that is followed. Now, I also said, I said this as at that time you would not even understand, but now you might know that better. I said it has a name. Do you remember what name? I said it has a mathematical name of the shape. Do you remember? I also wrote it, and then I arranged it, I think.
What was it?
Spherical truncated icosahedron.
Yeah.
Now that we saw icosahedron, probably you'll remember better. But I said it truncated. You know why spherical is because it's curved surface. But if you take the spherical out, it's a truncated icosahedron. Why is it called a truncated icosahedron? There's something common between this and this little thing here that you saw as icosahedron. Everybody knows what is icosahedron, right? This is the icosahedron, and you are going to make one using from the net. This is made of all the triangles. How many triangles? An icosahedron is made of 20 regular triangles or 20 equilateral triangles. It has 20 faces, 12 vertices, and 30 edges. Why do you think the soccer ball shape is called a truncated version of this?
What does truncated mean?
Truncated means you cut something off.
Oh, you're cutting off like the edges, not the points.
You're pretty close. So what we do is, if you take each of the vertex, what happens if you make a plain cut at the vertex? What shape do you think it comes? There are 5 edges going out at each vertex, right? When you cut it, you will now have pentagon there. You see? Because there are 5 edges and 5 faces, it makes a small pentagon. How many pentagons will be there? Because there are 20 faces. There are 12 vertices. At each vertex we are making a cut. Because the 12 vertices, there will be 12 pentagons. Right? Now, what happens to the triangular faces? When you make a cut at each triangular face, you will have one vertex here, one vertex here, one here. You will end up with 6 vertices. So you make a hexagon. So each of the triangle will become a hexagon now. How many triangles? Because there are 20 original triangular faces on this, now you will end up with 20 hexagonal faces. Okay? So you will have 12 pentagons and 20 hexagons. That's exactly we get this. So it's very easy to get this. Take this and cut a parallel cut at each of the 12 vertices, and you will get a truncated. That's why it's called a truncated icosahedron. That's how footballs are made. Do you think so? They'll probably make with this and make cuts like this. No, they don't make it like that. Mathematically you can get that, but they actually stitch it together in a factory. But mathematically speaking, so next time, any of you play soccer? You play soccer, right? When you go for a soccer game, ask your friends, do you know what is the shape of this soccer ball? Say, this is called spherical truncated icosahedron. And your football coach, for a second they'll think you're crazy, but then if you explain, they may not understand, but they'll get impressed. Okay? That's what it is. Okay, or you can go to the Brazilian soccer fans and tell them about truncated spherical icosahedrons. Okay? Now, how many, now that we said there are 5 Platonic solids, right? How many Archimedean solids do you think are there? Possible. Okay, guesses out of 5. Good guess. Anything else? Just guess.
10.
10. Another guess, okay?
7.
7.
Any hadrons that are not regular, that are not
You think every polyhedron that is not a Platonic solid is an Archimedean solid?
Yes, sir.
No, you can have. For example, do you think, you saw a 6th one here, right, on our dice? Do you think this is a Archimedean solid? Does it meet these conditions? It is not made of regular polygons. See, it is still made of regular polygons, except that they are not the same regular polygons. So not every polyhedron is, if it is not a Platonic solid, it is an Archimedean solid. Because you can have irregular polyhedrons, which are neither Platonic solid nor Archimedean solids. There are actually 13, there are exactly 13 Archimedean solids.
13 or
13, 1, 3.
Oh.
And this is the most famous of them all. The
Is there an infinite number of polygons?
polygons, yeah, because you can keep making as many as you want. You can
But
even
will
find,
they turn more circular?
yes. As you increase the number of sides of a polygon, it will become circle. Similarly, as you increase the number of faces of a polyhedron, it looks more and more closer to a sphere. You can also see just with 32 faces, this is pretty much close to a sphere. But if you take it to 100 faces, or 1,000 faces, or 1,000,000 faces, or mathematically speaking, a trillion faces, now that's a sphere. Because every sphere is made of some points, and every point is very close to being a small polygon. Right? Okay. So the 13, if we go to this drop down here, this is what you're seeing right now. This is actually the truncated icosahedron. See? That is actually the soccer ball shape. But if you go to the drop down, there are 13 shapes there. And you can go to the first one that's called cuboctahedron. We saw this earlier in a video. I said, remember this will come back to this. This is made of equilateral triangles and squares. So it's made of 2, and we can rotate them and see in different directions. So this is made of equilateral triangles and cubes. This is 1. You can go to another shape. Let's go to great rhombicoidecahedron. Yeah. So this is made of pentagons, squares, and dodecahedrons. Yeah, that's dodecahedron.
Great.
The bigger one is going to great wrong bicaso dodecahedron.
Looks really interesting.
Yeah, let's go to another drop down. But of all these, most famous one is probably the truncated icosahedron. Don't worry about that. That's the soccer ball shape. Not just because of the soccer ball, it is also found in nature. It is found in actually one element, one molecule known as C60. It is a variation of carbon. Did you guys hear about carbon? Carbon is one of the natural chemical elements. It is a molecule called C60 where 60 carbon atoms come together to make a molecule. And that exactly follows a truncated icosahedron shape. And this was found by, in fact, two scientists who got a Nobel Prize in chemistry in 1992 for finding that. Pretty impressive, right? And there are many applications for this in chemistry and in life. Okay? But there's one person who spent a lot of time. By the way, there's a name for this. This is called fullerene. This is going to be your second project, fullerene. And then I'll give you handouts. It's there in there. The fullerene is a molecule, a variation of carbon called C60, and it actually follows this shape. And the reason why it's called fullerene is it's named after another person called Buckminster Fuller. That his name is Fuller. His last name is Fuller. And he spent a lot of time on regular polyhedrons. And in fact, he kind of specialized in how to build what you call geodomes. Make domes or architectural things. Did you guys, anybody visited Epcot in Disney? Do you guys remember any regular polyhedron, big regular polyhedron there?
Yeah, I just visited last week. So
Yeah, remember that?
Yeah.
The big regular polyhedron there?
Circle, the big silver circle.
It's not circle, it looks like circle. They're actually polyhedrons. There are polygons made of so it's a polyhedron. So, the Buckminster Fuller is actually one of the pioneers in that, of how to build, they're called geodomes. Building domes using different combinations of polygons, regular polygons. And for so this particular molecule, when it was invented, is named after him. Now your second project is going to be do some research and find about it. What is special about fullerene? What are some of its characteristics in terms of the weight, structure, and why did the scientists get the Nobel Prize for that? Okay, that's more of a research project. The first one is actually more construction, but you can take your parents' help in both ones to do a little bit. Okay. Isn't that interesting? And maybe you can find more types outside of Platonic solids and Archimedean solids, and maybe you can invent upper Nine solids in the future. Yes?
For the research project, are we supposed to write an essay?
Yeah, you're supposed to write. You can use I'm going to give a handout, but you probably don't have more to write. You can take an additional paper and write it. Okay? Now, before we close, let's go back to one interesting aspect that we kept touching, this F plus V minus E. What is so interesting? What is so special about it? Right? Why is it always true for this? Okay. I don't know why it is always true, but this was first observed by a mathematician. His name is Euler. Now it spells like Euclid, but it's pronounced completely different. It's E-U-L-E-R, but you're not going to call him Euler. He's Euler. It's like Euler. Euler. Okay, that's how it's pronounced. He's a Swiss mathematician. He's a very famous 17th century Swiss mathematician. He's one of my favorite mathematicians. He actually he spent all his time on mathematics. Over 60 years of his working life just doing mathematics. And he did a lot of research, but he also studied a lot of previous mathematics from other mathematicians, summarized, he wrote lots of books. and he made it easier for others to read, because sometimes mathematicians, scientists, particularly in the old days, but even sometimes even now, right, they don't necessarily write in a way others can easily understand, right? It's very hard sometimes. He actually wrote many books so that others can easily understand it. He gave notations that we can easily follow, and many of his notations are still followed. There's actually a special letter named after him, which a special symbol, just like pi. Pi is a mathematical symbol, right? There is a symbol called E, which you will learn later. There's actually a famous formula called E equals e power I pi or negative I pi, I forgot, equals 1. That's called a unity. But don't worry about that. But the E is named after Euler. It is also, this particular expression called F plus V minus E is called Euler's characteristic of solid objects, or Euler's characteristic of polyhedrons. And it's very interesting. He first observed that for most of the polyhedrons that we see today in real life, and they are called convex polyhedrons. I did not say so far, but if you observe carefully, you can call all of these convex polyhedrons. Do you know why? Why can we call them convex? Do you know what is convex means? Now, some of you have glasses. I have glasses, right? Glasses are of two types. They're either convex or concave. Convex means it's kind of curved out. Concave means it's kind of curved in. Okay? Similarly, if you look at any of these, if the vertices are kind of going out, they're called convex. But you can also have something that is going inside and coming out, right? That we call concave. But most of the polyhedrons that we see in nature or in life are they're convex. And for all convex polyhedrons, this Euler's characteristic is always 2. F, number of faces plus number of vertices minus number of edges is always 2. That is not necessarily true for concave polyhedrons. And probably you can do some research about that. Although I did not do a specific project, but it's very, very interesting. There are people who spend a lot of time on this. And this kind of, whatever you're learning today, obviously is very interesting, fun. It brings out the beauty of math. But if any of you pursue any advanced competition math, for example, okay, you will find a lot of questions that requires you to use your imagination, using solid geometry. The thing with solid geometry is, if you don't ever spend time on this, usually you don't spend much time on things like in school, when a question is asked, it asks or it gives you this is a kind of shape. Let's say even if you take a cube and you make a cut like this, what will be its area? It's very difficult to imagine. This will help you build your imagination. And it's also helps in building what we call spatial skills. Ability to think in space. Even when an image is not given, when somebody is giving directions and how to go, right? That's part of spatial skills. But these are three-dimensional spatial skills. So it will be very useful if you follow any of the competition math, or even in future when you go to SAT math, etc. But forget about that, it's a lot of fun, right? So have fun with this. And if you spend time and have fun with this, you would love math, okay? So do math, not just because your teacher asked you to do, your mom asked you to do, your dad asked you, because it's fun, it's beautiful. But to find the beauty, you need to take one more step. You need to study a little bit more. And now that hopefully these projects will help you build that, okay? Don't just read, listen to this, go home and forget everything. Do the projects with fun and build those. And find more about Euler's characteristic, find more about Archimedean solids, find more about full ring, okay? And truncated spherical icosahedron, and why the sacral ball is like that, okay?